In this problem, we're asked to consider how will an increase in temperature affect each of the following equilibria, and we're also asked to consider how will a decrease in the volume of the reaction vessel affect each. So I'm going to go through and do a temperature for each, and the first thing you want to do is identify whether heat is a product or a reactant. So what we can see here is that this is delta H positive. So what that means is that for our first reaction here, that heat is a product of this heat is a reactant here. The system is taking in heat. So heat is a reactant. There we go. We are adding heat. That's why we've got a positive number there. So what does that mean? When the temperature goes up, we're adding a reactant, which means that the equilibrium will shift to the right. So that's what we can tell there. Okay, we'll come back and do the temperature in a moment. Let's go on and look at the next one. So we've got N2 plus O2 gives 2NO, and again we can see that this has a positive delta H, which means that heat is a reactant. So if the temperature goes up, that's the equivalent of adding a reactant, so that's going to cause the equilibrium to shift to the right. Okay, in the case of C, gets a little exciting because now we've got a negative delta H. So negative delta H means that heat is a product. So if I raise the temperature, I'm adding a product, and that will shift the equilibrium to the left. Okay, so let's have a look at D now. That'll be our last one. And in D, again, it is exothermic. We've got a negative delta H there. So we've got CaO plus CO2 in equilibrium with CaCO3, and heat is a product because that guy has a negative enthalpy. So when the temperature goes up, that's the equivalent of adding a product, and that's going to cause the equilibrium to shift to the left. So we do need to be mindful that at this point we've only answered half the question, because it also talks about a decrease in volume. And when we're trying to figure out how the volume is going to affect the equilibrium, what we have to do is to consider the number of moles of gas on each side of the equation. So I'm going to want to go in here and I'm going to want to add some gas labels in and make sure I'm confident about how many moles of gas I've got on each side of my equation, because that's going to determine how these systems are affected. Now, the calcium oxide is a solid, the CO2 is a gas, but the calcium carbonate is a solid. So you need to be a little bit mindful of paying attention to those phase labels. So let me just kind of get rid of this stuff about the temperature. And then we'll start looking at this. So we're going to decrease the volume. When you decrease the volume of a container containing gases, it makes the pressure go up. So the response of our system is it's going to decrease our number of moles of gas to make the pressure go back down again. So what way will it shift? It'll shift towards the side that has the lower number of moles of gas. So in our first case, we've got 2 moles of gas on the left and we've got 4 moles of gas on the right. So it's going to shift to the left. Again, the pressure is going to go up because we reduce the volume. So therefore, we want the number of moles of gas to go down to restore the equilibrium. Now, in this case, we've got 2 moles of gas on the left and we've also got 2 moles of gas on the right. So there's not going to be any shift in the position of equilibrium because there is nothing to be gained by doing so. Okay, so again, we're going to reduce the volume and that'll make the pressure go up. So the system will respond by reducing the number of moles of gas to get the pressure to go back down. So in this case, we've got 2 moles of gas on the left and we've got 3 moles of gas on the right. So it'll shift to the left to make the pressure go down. So again, we're going to decrease our volume. That'll make the pressure go up. The system will respond by reducing the number of moles of gas to get the pressure to go down again. So what way is it going to move? Well, we've got 1 mole of gas on the left and we've got none on the right. So it'll shift to the right. So that's fairly tricky concepts with respect to Le Chatelier's principle. Okay, so now we're going to look at Le Chatelier's principle again, but this time we're going to add like different chemicals to the equilibrium and see how it moves things around. So remember, we can change the concentrations of our reactants or products either by adding reactant or adding product, or we can remove product or add product or remove reactant. But what we want to keep in mind is that we can do the removal in a couple of ways. One is we can physically remove the substance, but the other thing that we can do is we actually can add something that will react with the substance, and we're going to see that right now. So it says ammonia is a weak base that reacts with water according to this equation. Ammonia plus liquid water gives ammonium ion and hydroxide ion. And then it asks a series of questions. It says, will any of the following increase the percent of ammonia that is converted to the ammonium ion? So we want to think about what that means. That means, will any of the following shift the equilibrium to the right, converting ammonia to ammonium ion? So if I add sodium hydroxide, what am I really doing? This is in an aqueous solution. What I'm going to be doing is I'm going to be adding, because that is an ionic compound, it'll dissociate, sodium ions and hydroxide ions. And you can see that hydroxide ions appear on the right hand side of this equation. So adding sodium hydroxide increases the concentration of hydroxide ions, and that's going to shift everything to the left. So the answer for that guy is no, that's not going to shift things to the right. Now, what about adding HCl? When we look up here, we don't see any chloride ions, we don't see any hydrogen ions, we don't see any HCl molecules in there. But what we need to recognize is that when we add HCl, this is a strong acid. It will react with the hydroxide ions to form water and chloride ion. And so what does that mean? Well, what it's going to do is it's going to consume hydroxide ion. So it's going to take away the hydroxide ions, and that's going to result in a shift to the right as the system replaces those hydroxide ions and reattains equilibrium. Now, what about when we add ammonium chloride? Well, this is very similar to what happened in example A. So ammonium chloride is an ionic compound which will dissociate to form ammonium ions and the chloride ion. Now, the chloride ion does not appear in our equation up there, but the ammonium ion does on the right-hand side. So adding ammonium chloride is the same as adding a source of ammonium ions, and that's going to cause the equilibrium to shift to the left. So again, no, this will not increase the number of moles of ammonia that dissociates into ammonium. In fact, it will have the opposite effect. So the only one that is going to cause an increase in the number of moles of ammonia that react with water is B, and the reason that happens is because the HCl reacts with the hydroxide ion, removing it, and then the system moves to the right to replace those hydroxide ions that were consumed. So the next question, 46, is in a similar kind of bent. It's about Le Chatelier's principle as well, but it includes for the first time some information about, it includes in the equilibria a solid. And so what we want to recognize is that the concentration of solids doesn't change. So we kind of need to be aware of that. This reaction is also exothermic, and it's going to be sensitive to temperature changes. So it describes here, it says, suggests two ways in which the equilibrium concentration of silver ions can be reduced in a solution of sodium ions, chloride ions, silver ions, and nitrate ions in contact with solid silver chloride. So you've got to have two ways. So for me, the first thing that kind of like comes up is like, think about the temperature, right? So this is a exothermic reaction, which means that heat is a product. So I'm just going to write this vertically to save some space because it's kind of long-winded. And what we want to keep in mind is that heat is a product. So our first way that we could get this reaction to produce or to consume silver ions would be to mess with the temperature to get it to shift towards products. So we want it to shift to the right? That's what we want, shift right. And how are we going to get that to do that? Well, if I took heat away, then it would seek to replace that product. So I could lower the temperature, take the heat away, and then the system would move to the right to replace it, consuming silver ions in the process. Okay, how else could I get the system to move to the right? Well, I think it's important to realize that the sodium ions and the nitrate ions are not relevant because they actually just cancel out. So that's not really going to help. But another way that I could shift this to the right would be to add a source of, you guessed it, chloride ions. So maybe something like sodium chloride, and then I would raise the concentration of the chloride ion, and then the system would want to consume those chloride ions by shifting to the right, and that would consume silver ions. So adding a source of chloride ions would be another way of moving this equilibrium to the right-hand side. Okay. So I'm going to stop there, and then I'll make another video with some of the more quantitative problems you were interested in.